So your test, my friend, is going to be a simple one. The first, Andrew, my friend, your test is going to be out of 2 questions only. This test, only 2. The calc, yep. The test calc will be 2 questions. One, it's about transformers, the most important transformer that you can encounter. That's a transformer. And the second one, so one about transformer, and the second one is going to be about a building, doing a load calculation for a building. I did not do anything about welders and so forth, but the welders and a couple of calculations will be on the final, guys. So on this test, I just picked the most important things that we did. Number 1, transformer, which is the most important transformer, and number 2, number 2 is the building. Number 1 and number 2. Cool? Anybody has any issues with that? So we talked about this one, guys. We said delta Y transformer are the most common transformers you're going to encounter. We have a system that's 480 in the primary, 280 in the secondary. I have 1000 kVA, 1000 kVA, and the impedance is 4. The impedance is 4%. And we need to find the following. We need to find the primary currents and fuses, the secondary currents and fuses, and I think we're doing also the main bonding jumper. Primary current and fuses, the secondary current and fuses, and the main bonding jumper and the grounding electrode conductor. So I can label them probably if I use a different color here. So we're going to do primary conductors, as you probably guys know, this will be number 1, and then we're going to have a fuses for each one of them. This will be primary. Oh no, this is not. We'll have the voltages first, and then we'll size the rest of them. Okay, never mind. I'm not going to mark them, but we will be sizing the fuses, guys, for each one of them. For each one of these, the fuses and or the circuit breakers plus the conductors. Okay, cool. 4% is the impedance. Z, the 4% is the Z right here. Z equal 4%. So we need to find a couple of voltages and a couple of currents and size the system. Couple of voltages, couple of currents, and size the system. Okay, any comments, guys, about these? So I threw a couple of coil and current. We don't get involved too much in the coil, FYI only. The coil current is the one that goes right through the coil here. The line current is the one that you always deal with, guys, the ones that are coming into the transformer. Does that make sense? Line currents are all what we deal with. We don't deal with the coil current. Okay, so let's go ahead. To find the primary line current, what do you guys do? You find, let's use a different color here. You find I line primary, which is for the transformer rules. What's a transformer rule? You take the KVA, divide this by 1.73, times it by the voltage line to line. Remember that? Line to line. Oh, it's line. When you go there, what's my KVA? 1000K. Divide this by, I think I'm not missing a 0 here. Okay, 100 by, yep. Divide this one by 1.73 times the voltage is 480. What do you guys come up with? Any calculator handy? Anyone? Did you come up with 1204 amps? Anybody came up with a 1204 amps? Second? Okay, so that's a primary current. This is the current that's going to go right through this. Morning. That's going to go right through this cable. The primary current. Any question guys about the primary current? Piece of cake? Piece of cake. We just started here. The primary current. Probably picture for us here. This is phase C, and this is my phase AB. This is my phase C, and these are. There we go. Picture a little bit more. Phase A. This is question number 1. Question number 1. All the phases. Any question, guys, about how to find the current? Is that piece of cake? Shall we go to the next step? Primary current coil. Primary current coil. Anybody remember the rules between the primary and secondary current? I primary coil equal I primary line divided by what? 1.73. These are the rule of the delta. Really, the reason why I threw the primary coil current, because it confuses the people. For the transformer, there are two currents: one primary coil and one primary line. And which one of them are you going to be using to size the conductors and the fuses? Anybody? The line all the time. That's the reason why I threw the coil, because when you're going to hear people talk about the coil current is meaningless in terms of sizing the fuses and the circuit breakers. So that's the reason why I threw this one for you. So if you take 204 and divide this one by what's the 1.73? Anybody can come up with a nice number? 696. 696 amps. The only reason why I threw the primary coil, just to remind you that when you deal with the transformer and you hear the current, the primary current, there are two primary currents. There's one coil, one line. The one that dear to my heart and yours should be that line. Why? Because the line is the one that we size the overconduction device and the conductors based on. So that's why I always highlight this. Oops. I always highlight this current. That's the most important current that I want to be using to use calculation. Any comments, guys? Any questions? Piece of cake? Okay. Let me know, Jimmy, when you're ready. I can flip. Good. Okay. I can. It's PDF too. Okay. So that's the primary. The secondary line current. Anybody can give me what the secondary line current is? Secondary line current. The same thing. KVA divided by 1.73 times V secondary line to line, and this will give me, what was it, 1000K divided by 1.73 times, what's the voltage on the secondary side? 208. Any suggestion? 2777. I have 2777. 2777 amps. 277777. 2777. 3 sevens. 2077. What a number, huh? Did we do the math right though? Slightly, give or take 8. We're not going to fight over an amp on a system that's 3000 amp. Yep, you did the ratio. You could do the voltage ratio too and find it. Now the secondary current, I want to remind you guys, when it comes to the secondary current, the transformer is a delta here. That's why we divide it by 1.73. On the primary side, the transformer is what? A 1. So the secondary current, I secondary, the current here, I secondary coil is the same as I secondary line. Everybody understand that? Same thing. There's nothing, there's no, the current that comes out of this coil is the same current that goes into the line. Can I have thumbs up, Chad? Piece of cake. Let's review a few of the stuff that you guys did with us before. So what's the I secondary coil equal I secondary line equal 2 NS7 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 amp. Why? Because it's delta connection. Delta is the first one. You're absolutely right. It's a Y connection because it's Y connection. Y connection. The one before that, let me just write right next to it so you remind yourself, guys. The reason why we did here because it's a delta connection, right? Delta. The rules for the delta connection. Cool. So delta connection, Y connection. As always, I'm going to highlight this value here. This value here. And this is the value that we always use to size the fuses and the circuit breaker. In this case, they're the same, but they don't have to. Okay. That's my daughter.
Oh. I was like, did I have a chance to ask?
Any questions guys about this? Any questions? So since this transformer is not tied to a panel, we don't know what the load on it, right? Remember, if it was tied to a panel, we sized it yesterday without 1.25. Since it's not tied, we don't know what's tied to it. We're going to size it based on 1.25. So primary feeder, the primary feeder, guys, you take 1.25, multiply, what was the primary current? 1204. Thank you, sir. 1204, and that will give you a healthy or non-healthy. So when you multiply that one, anybody did that? I came up with 1505. Thank you, 1505 amps. That's step one. Step two is to find the conductors, right? So 1505, I don't think you can carry that boy with one conductor, can you? So what are you going to do? How are you going to parallel it? Remember, the rule is, when you parallel, try to hover over 400 amps. So what's the number that you divided by, divide the 1505 by to get you close to a 400 amp? So 3, 4, I use 4. You can use 3. 3, I think, probably give you 600 amp, 600 kVA. But I decided, now on the test, if you did 3, would it be wrong? No. Okay, so divided by 5. When we did that one, it gave me a value of 376 amps. Cool?
Divided by 5. By 4.
Divided by, thank you, divided by 4.
Can we come through that in even numbers?
No, divide by, no. You can divide by 5 or 3, no, doesn't have to be even numbers. Yeah, no, it doesn't have to be even numbers. Then you go to table 310.15 B16 under which column? 75-degree column. And you will get the following. How many sets? 5 sets of what?
4 cents.
Why am I stuck with the number 5 today? 4 sets. Thank you. 4 sets of how many conductors? Anybody came up with the size? How many conductors and what size? And why? Okay, the conductors are 500. How many conductors though? That's easy to answer. Is it 3 or 4? Why 3? It's a delta, no neutral. So 3 conductors, 500 kcm, T, H, H, N. 5 sets of 3 conductors, 500 kcm. Joe, because we have a delta, the delta take 3 phases, no neutral.
No, it's okay, please.
Well, it depends. It really is. If that one, the W is coming, if it's a wet location, we're assuming this transformer. So in the test, guys, if you put W, I'm not going to say wrong, but I want you to put an insulation though. Does that make sense? It really depends. So the W outside, most of the time, guys, they have THHN/THW, dual insulated, and it covers both sides. Any comments, any questions about that?
On the secondary line current work, you multiplied 1.73 times the secondary voltage, and then what's the L dash L?
This is secondary line to line. Line to line. The line voltage. Yeah. There's 2 voltages, the coil voltage, which is line to neutral, the line voltage, which is line to line. Did you guys do some calculation with Gary, fundamental calculation, most of us? And you did it with us, right? We did line to line, line to neutral, the fundamentals we call it. I don't touch on the fundamentals of motors. I assume you guys the first year, right? We do convert voltage primary to secondary. It comes, we just take the data and size things for it.
That's just one line, though, isn't
Yeah.
it? There's actually a big 3 sets, 4 sets. Because A, B, and C are all.
There will be 4 sets of 3 conductors, 500 kcm.
But that's just for the A phase.
There will be 4 sets for the A, 4 sets for the B, and 4 sets for the C. So a total of 4 times 3, 12 conductors. You will have 12 conductors as a total. So every phase is going to have 3 or 4 conductors in it. Right? Is that what paralleling is, guys? Everybody understand the paralleling? Yeah. Good point, though. Yes, sir.
2 questions actually. The secondary coil current is something with the phase current,
Because we are Y.
and how we determined that it was a Y.
Because you missed the diagram.
Well,
It was here.
story of my life.
If it's delta, we divided it by 1.73. Yeah, that's a diagram that you do. I have a PDF too. Okay, so it's delta Y. Any question, guys, about this? I didn't mean to make fun of it, just
Oh no, it's fine.
because it was drawn here,
My-
but
my fault.
yeah, not big, not big. Okay, any question, guys, about this? Shall we go to the secondary feeder? Now, I highlighted, guys, the cable that you use to size the conductors, right? This is always line, always line. Anybody knows why line? Because line is where the line is the feeder that's coming to the transformer, right? Okay, so secondary feeder. For my secondary feeder, I want to take number 6. I'm going to take 1.25. So the first step, multiply this boy by 2, 7, and 7, and 7, and get myself 347 amp. I don't know if you guys came up with something like that. 3471. Now that's a big boy. That's a big boy. Right? So second step is to parallel. Any suggestion for paralleling? 3, 4, 7, 1, divide by. Any suggestion how many sets? 9? 10 will be easier. So just move the easiest. That's why your friend Chad took 10. But if you do it 9 tomorrow on the test, and on Monday, it's okay.
8 is about 400.
Yeah. So if you take 10, this becomes 347.1 amps, right? And if you take this one to 347.1 amps, take this one to where? 310.15 B16 under 75-degree column. And this will give me the following. 10, oops. That'll give me 10 sets of how many conductors and why. 10 sets of 3 conductors, 500 kcm T H H N. What happened to the neutral? We're going to derate the neutral. What happened to the neutral? We're going to derate the neutral, right? Could I have gone with 4 sets, guys, and call it a day? Yes. That's what a lot of companies say. The heck with you. But it's expensive, though. So let's derate the neutral. Okay. I'm going to move this one down a little bit, the overcompression device, and so I can do the neutral. The neutral, I'm going to do it with the green. Neutral. For the neutral, I use the same value that we did for the phase, guys. I'll start with 3471. The first 200 amps, what do you do with them? Leave them alone. Anything higher? Anything higher than that, what do you do with them? 0.7, and give me the answer. I don't have the answer for this, so I need somebody to do it. Because last year I told them to put full neutral. I was generous. How much? Altogether. How much? 4490. 1 more time. 24. Thank you. 2490. Right? Right? Any second? Second. Okay. So here's my calculation. Now the second thing, guys, for the neutral is 2490. I have no other option now except to divide by what? 10. No options. You're locked. So I have 249 amps, right? And then you take the 249 amps, take him to table 310.15 B16, 75-degree column. What do you get? What do you get? You get how many? 5 sets.
10 cents.
Times 2. 10 sets. 10 sets of 250 any second of 1 conductor. 250 kcm THHN. THHN. Any question, guys? Makes sense? No? So that's your that's your neutral. I think the next page is we missed the overcome protection device. So I'm going to put the overcome protection device here. Okay. So we got secondary. I'm going to move these down a little bit so I can put my overcome protection device. The number 7. I'm missing number 7 here. So what I'm going to do, let me just see. I'll start with the number 7 here. Adjust my schedule, and that will be secondary overcurrent protection device. Am I drunk today? Primary overcurrent protection device. Thank you. I don't drink, that's the problem. Okay, here's the article for you, 450.3b, table 450.3b. Do you guys remember the multiplier? My multiplier was 2.5 times 1204 equal 3010 amps. Anybody disagree with that? Then next step, you take 3010 amp, take this one to 240.6, and what do you get? You have to go down if it's not standard, because the table tells you you can't go up. So your standard is 3000 amp. Disagreement? Any dis? Because the table doesn't say that you go up. Number 8. Secondary overcaptation device for number 8. Any question guys about the primary overcaptation device? So I have a 300 amp fuse or circuit breaker, it doesn't matter. 3000 amp. For the secondary, what you guys remember what we do for the secondary? 1.25 multiplied by, what was the amps for that boy?
2777.
Thank you. 2777. That will get you a healthy 3471 amp, right? And then the next step is to take the 3471 amps, take advantage of 240.6, and if it's not a standard, in this case, go up. And Aaron, do you remember why we go up? Because if you go to table, let's put the table. If you go to the same table here, table 450.3D, this table, it will tell you go up. There's a note number 1. Do you guys remember note number 1? It says go up. Huh? Please, when you guys go this one, always go to the table and see, does it have note number 1? Because in the test, I might give you different voltages. Always get into the habit, just go to this table and see, does it have note number 1 that says to go up or not? 430.50D. There is no D. There is no D. There is D. Thank you, buddy. What does it say? B. Number 9. Number 9, grounding electrode conductor, aka grounding the electrode conductor, right? Any question guys about the fuses? So we size the fuses, we size the cables, no problem. Now we need to go size the grounding electrode conductor. Any suggestion? How many sets on the, by the way, the grounding electrode conductor, here's the, take this, grounding electrode conductor guys, the grounding electrode conductor is going to be coming from here, that one here, going all the way to the ground. Not the primary. There is no grounding electrode conductor on the primary. It's always the secondary. Separated drive system, the secondary. Everybody understand? Since it's in the secondary, which cables am I supposed to use? The primary cables or the secondary cables? Since it's on the secondary. The secondary, right? Am I the only one who's slow today? If we have the grounding electrode conductor on the secondary, which conductor to use to size it? The secondary conductor, right? Thank you, my friend. So we go all the way, because when you come here, look what happened. Okay, which conductor am I going to multiply it by, Chad? The primary or the secondary? So we multiply by the secondary. So there were how many sets in the secondary, guys? There were 10, since we're paralleling, we have these 10 sets, multiplied it by 500, K, C, and M. That's easy math, 5000, comma, K, C, M. The next step, my friend, is you take the 5000, comma, KCM, take it to which table, Aaron? 250.6 and another 6, and that will get you healthy one conductor. What size? 3 aught. I got 3 aught too. 3 aught, A, W, and a G, and let's say T, H, H, N. Or THHW, or bare, or covered. This is a not carrying current. Any question, guys, about 9? Any question about 9? Any question about 9? Let me know when I can move to 10. Yes, no, good, okay. 10 is the main bonding jumper. Main bonding jumper, as you guys know, you take the same 10, multiply it by the same 500 K, C, and M. That will get you easy math, 0, 0, 0, K, C, M. Step number 2, you take the 5, 0, 0, 0, K, C, M. And is it more than 1100 KCM? If the answer is yes, right? The answer is yes. Then you proceed to step number 3. And step number 3 says, yeah, right? It's yes, it's more. You take 12.5% and you multiply this one by the 5000 KCM. Right? Are you guys following? We did that before, so straightforward. If it wasn't, by the way, if it wasn't more, you just go to 250.66 direct. Okay, and the arco for these main bonding jumper is 250. The arco for this is 250.28. I always like to write this one, 28D as in dog and 1. And comma also 250.66. These are where you get the info. 250.66 table, T for table, and section 250.28 D1. You guys know why we put any secret book articles? Because everybody has an opinion. That's why when I write things, it's an opinion. I put CSK. It's opinion. Because it could be right or wrong. This is code. Code is, the difference is, this is agreed upon opinion. You know, bunch of smarter than Chad and Brian guys sat together and said this is a best practice. That's what the code is. Otherwise, if it's not agreed upon in the code, it's an opinion. Okay, so anybody have a math for me here? 625 K, C, and M. Now I don't know about you guys, but 625 is not a standard size. Last time we checked, 625. So what do you need to do? 625 KCM. I know some of you will say we'll jump to 700, but it could be a size that you don't understand, you don't know. So you're going to go to chapter number 9, table number 8, to find the standard. 625. Our standard is 700, right? The next standard. And probably a lot of people look at it and know it's 700, but the rule is 700 K, C, and M. KCM. 700 KCM. What? That's question number 1. Shall we give you a few minutes for question number 2, or you will roll? Few minutes? Okay. 4%. 4%. I'm going to do the impedance. Yeah, there's one more thing.
Okay.
Can you hold your horses? Yeah. One more thing. I want to do the impedance here for you. Thank you. I forgot the impedance. Okay, the last thing on this is I'm going to put it right in here. And I'm going to make it number 11. Short circuit. I short circuit equal I secondary line divided by miss Z, the percentage of the impedance. What was the secondary the secondary line current? Was it the 2777, right? I have a 2 and a 7 and a 7 and a 7. Divide this by the impedance is 4%, which is in decimals 0.04, 4%, right? And that will give me, this is a Z, believe it or not, crooked one, crooked C. Anybody? I didn't do the math for this. 69 second, 69 point.
69.425.
Point, okay, 69.4 K KCM or kilo M? Kilo M. Kilo M. Yep, 69. So why this is important, the fuse that you guys just picked have to be rated to handle a 69,000 amps. So the next standard, they go 65. The next standard will be, typical standard is 85. So the next standard is 85,000. So it's a lot of short circuit amps, as you can see. Cool. Well, yeah, you don't have to remember this, but typically they go what 22.5. There's 35, 45 is coming. These are the most common ones. 22.5. And there's 35, 45, 65, and 85, and 200,000. These are very common. Don't know if they do 70, honestly. I have to check. But these are the most common ones that I've seen a lot. So from 6, yeah, if they make a 70, you go to 70. But how would I know? You're going to go to the literature of Kahler-Hammer. That's the only way. Kahler-Hammer square D, and go to the circuit breaker section. Do you guys remember when Todd was talking about this? You go to the section and you find the circuit breaker that gets you the short circuit or higher. Yeah. Okay, that's all. Let's take 5 minutes.
Well, it's hard for me to walk through the door.
Okay, now we're recording. Calm down. All right, moving on. Next question. Here's the next question, load calculation. If you graduate from here without knowing how to do load calculation, ask your friend Chad Kearney for a refund, will you? I'm not saying you're going to get it, but at least ask for it. There's a difference between asking for and getting things, right? When you guys have kids, you understand the difference, right? Between you can ask whatever you want to ask, you get what you get again.
The school gives you a refund, they can't afford my paper, so.
Commercial building. I have a commercial building. It's an office type. The voltage system is 480. The reason for the 480, can you guys see the area? Look at the area that we have. 50 kVA. Do you remember that cutoff that I told you make more sense to use 480? Anybody remember the cutoff? That was 15 kVA, 15 kV or higher, or 15,000 square feet or higher. So the voltage system is 480. I'll give you a few seconds, guys, to write this. I should have probably printed it for you. I apologize. The voltage system is 480-277. It's an office building, 3-phase. I have an AC that's burning at 15 horsepower. Actually, 15 ACs. Each one of them is 15 horsepower at 3-phase, 480. A heater that's running at 150 kVA. An area of 50,000 square feet. One sign, 200 track lights, 200 feet of track lights, 250 feet of multi-amp assembly, 250 receptacles, and computer load. This is new. Number 8 is new, guys, for you. I don't think we've done computer load, not this way. Computer load of 20 amps at 120 and 10 circuits. 10 circuit dedicated for data center. Yes, sir.
The question where you're saying that
Absolutely,
but it's gonna be above 15K then.
absolutely. If it's not, I will tell you what voltage is. I will tell you what voltage to use. So you don't have to make this decision. So I might tomorrow, I might throw 600 volt at you, or 208, or 240. So be very careful. The voltage is going to vary. Yeah, for the test, guys, all this data will vary, right? The only thing, but the material will be the same. So you'll have 20 air conditioning, 20 horsepower. Does that make sense? But the concept is the same. I'll give you a few seconds, guys, to write that. And I apologize, I should have copied this one for you, at least this one. But I was lazy today. No other excuse. The song before Zach. If Zach is here, we would have been done with it. With the copy. Where is Zach? Zach is not getting good. Why do you guys call him Zach?
That's how he spells me.
He said it one day. Z-A-C-H, so he said Zach one day.
No, the funny thing is that that's how somebody like me, bilingual people, that's how I would say it if I don't know it. You know what I mean?
Kind of like Geoff. Yeah. Those weird guys, G-O-F-F.
No, Michael, like Michael, right? Like, if you don't know it's Michael, that's how I used to say it before I got used to the names, Michael. Okay, any question guys about these? Can you have thumbs up when you're done with these? Because if you leave it to Adam, he'll keep you busy for an hour here, just chatting. Okay, I can't emphasize, I boxed in this area because it's a new, I want you to pay attention to it, because we didn't do it. We did it slightly different in our load calculation. Cool? I'll take your time. Not really. Take your time, not really. Should have copied that one for you, guys, sorry. Because that's a lot of data on it. So the info will be guys like this on test, and you just do the calculation. Now tomorrow, do me a favor, Andrew. Step-by-step calculation if you want to have it. I don't want to see the examples, but if you have a list, what to do, where to go, to do things, I encourage you to do that. There's so much, guys, so much calculation. I dare anybody to memorize all the stuff that I'm going to throw at you, especially on the final when all these come together. So, yeah, that's why if
through it all, and then 6 months later, say you don't do a commercial load count for
Yeah.
4 months.
But you know what, Jeff, what I do and what you should do, you should keep the most important things that you got here. When I was in college, I kept all my books and all the stuff, honestly, because you can use it, but I guarantee you, if you have an example, it will refresh your mind immediately. Like the Excel sheet that you developed with me, the Excel sheet, you're gonna lose it probably 2 months from now if you don't use it. But if you go back to it, it refreshes your mind and you roll in. Okay, so let's go. Okay, so what's our goal? By the way, what's with all this? We're supposed to size a service for the building. That's the outcome. So the outcome of all this is to size the service for the building. Shall we go ahead and size it? Okay, so we're gonna size the service for the building. So I'm calling them, the first thing is general lighting. We're gonna do general lighting, guys. Okay, so let's go ahead and do the first calculation. It's gonna be my general lighting. I'm gonna use color. Which one is better for you to see? Is red good? Red is good. Okay. All right. So I have how many? So the first calculation is I have 50K square feet multiplied by what's the code allowance for light allowance for commercial building, office building. 50K for the 1,000 square feet multiplied by 3.5 from the NEC code book. And this is coming from 220.12, everybody, 220.12, multiplied by 1.25, that will get you a healthy 219 kVA. So the lighting allowances for the whole building based on NEC code book. Can you have thumbs up, Chad? Piece of cake. No gimmicks, nothing. No gimmicks, nothing. By the way, now do I have this step? Do I have actual fixtures to compare this number with? Do I have actual fixtures? If I don't have actual fixtures, I'm stuck with it. That's all mine. Cool. If you have actual fixtures like 100 lights, each one of them is 95 kVA, then you multiply 100 by 95, do the answer and compare it with this, pick the largest. Okay? All right, track lights. You guys remember how many feet of a track lights do I have? I have 200 feet of a track lights. The code says 200 feet of a track lights. Every 2 feet, you give it 150. That's why we divide by 2. Multiply this by 150. Everybody understand what I did? I took the number of feet, divided by 2 and multiplied by 150, because every 2 feet, you give it an allowance of 150 volt amp. And then, because it's continuous load, what do? Multiply it by 1.25. So that's, and this is coming from 2.43, I believe. That's 43. Track lights 220.43 B. Let me just do that one here. Give me 1 second here. Just write this one. This one coming from 220.43B. Which one? This one? This one is coming from 220.12. Let me do it for you. So this is coming from table 220.12. Cool? 220.12. Okay, so what's the answer for this one? Anybody came up with 19 kV and A? kVA. Anybody came up with that number? kVA. kVA. Okay, so that's this number. The sign. You guys remember the sign? The sign is, allowance for the sign is 1200. Multiply this by 1.25. And this is coming to 220.14F. F as in fun. Not the other F. 1.5 kVA.
Today is brought to you by the letter F.
You hear about the contractor in, I think it was in Rochester, got mad at MnDOT, and then he named all his vehicle FU MnDOT. FUM Min and dot MnDOT. So it was in the news for a couple of days. And then somebody interfered, and you know how those rich people say, shape up, man, shave on you.
Commercial vehicles, just freaking pull you over every time they see you.
I put down 220.14F. That's not a code reference, is it? That's
Yes.
Oh, is it?
Yeah.
220.14F.
220.14F. Yeah. Any comments, guys? Any question about these? Shall we move?
Yeah, that's a lot.
Why? I'm sorry. Why? What?
Where'd you get the 1200 from?
The 1200 is coming from 220.14F. If you go there, good point. Remember every sign, guys. Do you remember that the signs, you have one sign for a commercial building, allocate for this sign 20 amp circuit, and if you go to the sign, I think it's 600, it will tell you that it has to take 1200 volt amp. So this is coming fixed for one sign.
Continuous load.
Yeah, continuous load 1.25. Yep. Move on. All right, next. Before I move on, guys, I just want to highlight the ones I want to carry. Do you agree with me that this is the number that will be carried down all the way, right? There is no more derating on these three numbers, right? They all will be carried all the way down. Very important to know that. Let's go to the next step. Okay, heating and cooling. So I have my heating. What's my heat? My heat is already given as a lump sum 150 kVA. We care less what type of heaters they're using. They are lump summing it as 150 kVA. Okay? They're given, right? It's given. All lump summed. Given. Right? Now the air conditioning. My air conditioning is the issue. My air conditioning, I need to do the following. I take 115 horsepower. Remember, I have 15 horsepower. You're going to go take it to table 430.250 under 480 volt, 3 phase, right? And that will get you a 21 amps. Anybody disagree with that? If you take 15 horsepower, 240, to table 430.250 under 480 volt, which is in the table will be 460, right? The nominal 480, but the actual voltage in the code, operating voltage 460, a little bit less. Okay, so when you go there, that's step one you have to do. Step two, how many air conditioning do I have? 15. I should have picked a different number. So there's 15 of them. Each one of them is 15 horsepower. These don't get confused. There's 15 of them. Each one is 15 horsepower. So here's what you need to do. I lumped them in one. So I'm going to take 1.73 multiplied by, multiplied by, what's the voltage? 480 multiplied by, what's the amps that we came up with? 21, right? 21. Now, multiplied by 21. Cool. Now remember, these are motors. So I'm going to throw here multiplied by 1.25, that's the largest motor, plus, so this is the first motor. The second, how about the second motor? Then we the 14 times 1.73 times 480 times 21. I hope I didn't confuse you here. So you take the first motor, multiply it by 1.25, add the full load current of all the other motors. Do you see what I did, guys? I took the first motor, which is only one of them, multiplied by 1.25, assume it's continuous load, right? Because of the largest motor, plus the other motors. How many of the other motors if you take the first one? 40. I need somebody to give me the answer for this because my answer, any? Anybody has an answer for me?
For the top one, we got 21.8K.
Shall we, you know what, shall we do in 2 steps here? Let's do it in 2 steps. So here's, this will give me what? 21? 21.8. Okay. How about the second one? 244. Okay, right? Total? Okay, how much? 265, 265.8K. Okay. What did I come up with before? 261. Okay, 265.8. Everybody understand why we took the first largest motor, and then we summed them up. We added these two together. Oops, let me just put I added them. The first motor, then the second, the rest of them added up to 265. And then what do you do? From the last step, the last step, guys, is choose largest of heating slash cooling. The heating slash cooling, you choose the largest, and this is coming from 220.60. Anybody remember? I can't remember that. 220.60 somewhere. When you choose the largest of the heat and the cool. Heating and air conditioning. Well, not optional. Fixed electric. Non-coincidental load. What was that step? Check appliances, and I should have. Okay, 60. Yep, I'm right. 220.60. All right. So what's the largest? Between 150 and 265.8. 265.8. Right? Anybody disagree with that? So this is the number that you will be carrying downstream. This is the number for the two steps that you will be carrying downstream. Any questions about that? Okay. Shall we go? Next? Next? Everybody understand when they say choose largest of heat slash cool is we're looking at the 150 versus the 265.8, right? Cool? Right? The first motor is the largest.
Right.
Add 25 on it, and then add the rest of the motor to it.
Okay, yeah, but okay. Sorry, I was,
It's all right.
and so the 228.60, that's just the code reference that tells
Yep.
you to use the largest, and then what's 265.8?
265.8.
Oh, it's our total. Jesus Christ.
It's all right. That's all right.
It's Friday.
That's all right. I'm sorry?
No, just the NEC code for the 1.25 for one.
Yeah, the motors. You guys have the whole references. Yep. The largest motor. I can't remember, was it that I gave you before? 430.2. Okay, you guys have, I don't want to focus too much on them because you have them in load calc. All these references, you have them in the load calc. I just do the most important ones that need you to do the work. Okay, let's go to F. F is computer load. Your computer load, here's what the F does. I have 20 amp multiplied by 120 volts multiplied by 10 of them, because there's 10 of them. These are computer load. These are computer load. What's a computer load? Computer load servers, like these. Servers, they're plugging in, this is router, but servers plugged in at all times, crunching numbers. So we debated multiplied by 1.25 for continuous load or not. I think this is good enough. And so computer load, I don't have reference for it. So if you multiply all of them together, assume it's the continuous already included in the 20 amp. That will get me, for F, that will give me 24. 24 K, B, and A.
So it's just a straight multiplication.
Yep, 20 amp circuit, 120 volt multiplied by 10 of them. So you have 10 circuits coming from a panel that dedicated to servers. The way we did the calculation for our server, Jeff, if you remember, the square foot multiplied by, I can't remember what the 90, I think I gave you. Well, so yeah, I don't think we did we do load, computer load for this project? It was the second project that we did computer load. I don't think we did computer load. Next project we'll do it. 24 kVA. All what you have to do is just multiply the voltage by the amps by how many circuits you have. Cool? Then you carry it all the way through. Receptacles. Let's talk about receptacles. So how many receptacles do I have? 250 receptacles. Multiply them by each receptacle 180. That will get you 45 kVA. Multi-outlet assembly. Multi-outlet assembly. This is coming, by the way, from 220.14i. Multi-outlet assembly. Does it say continuous on it? No, if it doesn't say continuous, it's not continuous. So I have 50 feet divided by 5, multiply this by 180. That will give you 1.8 kVA. Cool. Now add them up. That will get you 46.8 kVA. 46.8 kVA. Add them up, the two. Then the last step, these are the two steps. Then we need to demand them. Demand. When we do the demand, guys, we're going to take the 46.8K, take him to this table, table 220.4 and another 4, and here's what you're going to get when you go there. You're going to get the first thing K, leave him alone. Anything higher than 10, what do you do with them? 4, 6.8 minus 10. What do you need to do with this? 0.7. You have to multiply by 7 and add them up. Remember how we, I'm sorry, not by 0.5. We cut them by 0.5. I'm taking them the neutral. 0.5. Oh, wow. How did that go? Gosh. 0.5. Cool? 0.5. Wow. Okay, so, and then that will get you a 29, right? 29 kVA. 29 kVA. This is for G, step G1. So I have 29 kVA, the demand. 29 kVA. Any question, guys, about the 29 kVA? Yeah. Yeah.
23.4 plus 10. So, oh, 30. Yeah, right.
Cut this by half.
I didn't subtract the 10.
Yeah. And then you add the 10, 29, right? Right? Math is right? Okay. Now, so we demanded it. Then we have to compare them, guys. The next, we're not going to carry it yet. Next, we're going to take receptacle based on the NDC code book for a commercial building. That will take 50,000 square foot, multiply this by 1 from the NDC code book. That will get you a healthy 50 kVA. Okay? Then you have to choose the largest of G1 or G2. Everybody knows what G1 or G2, which is basically the code or the actual. You're going to choose the largest for the receptacle of the code or the actual. And in this case, which one was the largest? The code. So that for this step then, 50 kVA is the number that I'm going to carry downstream, and I put asterisk by it. Does that make sense? You do the calculation based on the code and based on what Joe had designed and through receptacles, and you pick the largest of the two. You pick the largest of the two. That's a piece of cake, huh? Almost done. Okay, so these are all the receptacle, all the loads that we have. So the next step, guys, is a building demand load. They ask you about the building demand load, which is basically you're going to go back and add all the stuff. So you start here. We're going to add all the stuff that we put the asterisk next to it, right? The demand for the light, the track light, the sign light, we're going to add them up. Then the heat and the cool, right? Right here, heat, cool. And then we're going to do the computer. Then we're going to go the receptacle demand. So I want to go add them up. So let's go. I have 219, that was, I believe, for the lights, plus 19, plus 1.5, that's the sign. That's not a good plus. Plus, you add them up, plus 265.8. I need somebody to help me with them because plus 50 equal. Can somebody give me the answer for this? 555.
You're missing one.
What am I missing?
Computer load.
Which is 24.
24.
Thank you. Plus 24. Thank you. That's what it doesn't. 24. Okay, now add 579. That sounds about right. 579.3 kVA. This is my demand for the whole building. 2 second. Did you guys get a second? Okay. 579.3 kVA. Cool. This is when you go size your transformer, if you have control over it, to get you this amount of kVA. You know what happened? Right here. So you're looking at 579.3. Now, Joe, you give this to Excel. Guess what they do? Take this number, cut it by half, and give you a transformer outside. Half to 2/3. And they call this calculation architectural calculation, because it's way oversized. We've done that all the time. So the rule of thumb, when you send it to Excel, this calculation, they chop it by half, between half and 2/3. That's what they give you of what this number. But we're not the utility though. If you give it to Brian, he will give you 4. Would you give him 4, Brian, when they come to you? Then we need to find the current, guys, because we size things based on the current. 579.3 K. Divide this. What's the voltage system? 1.73 times 480. We're burning them at 480. I need somebody to give me the answer because that my answer is screwed here too. 579.3. 698 amps. Do I have a second?
Here.
698.
I put you in the lab here.
Ouch. Yep, second. Okay, thank you. So what's the answer here? 697 amps. Right? Or 698? We're not going to fight over an amp, are we?
No, we just want to be good.
698 here. Okay. Let's just fight over an amp, huh? 698. 698 amps. Okay, any question, guys? 698. Now I'm going to show you. I'm going to show you guys, gentlemen, calm down, calm down. I'm going to show you it doesn't make a difference here in a second. So the overcome protection device, you're going to take the 698 or the 697 to 40.6. 698 or 697, what's the standard overcome protection device? You're gonna go up to what's next? 700. So did it really make a difference?
Huge difference.
You end up with the same panel anyway. See what I mean? That's 1 amp, but doesn't make a whole lot of difference. Plus or minus 1 amp, not a big deal.
700 to 701.
Then I go, now that's where you use your judgment. Then you go down. See what I mean? Plus or minus an amp doesn't make a whole lot of difference. Okay, so what's my service then? 700 amp service. 700 amp service. Okay, so this is my service. What did they do here? Did they move something? How the heck did I move these up? I just moved these. You can move them. Yeah, I think you can. You can drag it, see? Isn't that cool? I don't use a lot of these, but they call them smart board. You don't call them Chad, do they? They man. This is not Daniel size. This is panel size. Okay, but the P got erased when I erased that. So this would be a panel size. We put the stick for it down
That
here.
was a nice move right there. I saw that.
Uh,
You're gonna write like over here, so the line would draw right here. I love that calibration.
I calibrated at the beginning, but after a while you lose your calibration. You have to keep calibrating. Okay, what's the panel size? When we size the panel, we have the overconduction device. Then we need to take the same, what was it, 600, 698. Take it this time to D Walt. And this is 3-13. What's the next standard panel? The panel. 800 amp. So you have a 700 amp circuit breaker and an 800 amp panel. Is that okay? There's nothing wrong with that. Now they give it to somebody like Andrew and say, you know what? I'm going to match my panel. So I get the full capacity of my panel and I make an 800 amp circuit breaker and I'm oversized B it. Is that wrong? No. The smart engineer or designer guys always match the overconduction device to the size of their panel. So, but if you're too far away from that, that's where it becomes kind of a cost saving issues.
Gives you 10% feature growth.
Yeah, if you win there. But for the Chad, we're going to stick with the code. Okay, so where are we here? We're at the panel size, feeder size. Feeder size, we always say for feeders, match overcurrent protection device. You can't go wrong by matching the overcurrent protection device. So, my overcurrent protection device is 700. I don't know about you guys, but 700 is a lot of amps to carry in one feeder. So I'm going to go parallel 2. Would they hurt anybody's feeling if we cut it by 2? So that will give me 350 amp, right? And then you take it from here to where? You take it to table 310.15 B16 under 75-degree column. Is what you get. You get the following. You get 2 sets of how many conductors? Of how many conductors? 3 conductors. What's the size? 500 kcm. What insulation? THH. Let's say W this time to be different. Cool. We're going to derate the neutral. I want to derate the neutral. And I will come back to the main bonding jumper, but I'm going to derate the neutral this time. So then we come to neutral. Okay, for neutral, since we size everything based on the 700, guys, use the 700 because we size the feeders based on 700, right? Not based on the load. Use the 700. So let's start. My start point would be my 700, unless for this one, guys, here's what I tell you. Unless you want to go and eliminate like we did it in the proper way. Let me tell you the proper way. The proper way is to go and eliminate all the neutrals that we did, and all the loads. Yeah, the three-phase neutral. In this case, probably would make a lot of sense to do it this way because we have full control over the load. But if you don't know what your load is, let me tell you, if you just don't, all what you have is just a lump sum panel, and you want to size a neutral for it, you just take the 200 plus 70% of everything higher than that. But since I already know my neutral load, let's go at it. So let's, can somebody give me the neutral load? So let's look at the first load was the receptacle, right? Was the receptacle load a neutral load? Let's go back and look at them right here. Neutral load, neutral load, neutral load. Okay. All right. Is this a neutral load? Is this a neutral load? So I want to put neutral here. That's one like an check. So I have my neutral. Okay. All right. So is this a neutral load? Track light. And is this a neutral load? Yep. Most likely. So let's go to this. Heating. Is this neutral load? No, this is not neutral load. Because this is all 480. Computer. Is this neutral load? No. And neutral load. Receptacles. Is this neutral load? Yep. So go back to receptacle. This is a neutral load. Okay. So the only thing that was excluded from the whole mess here is what? Is really the air conditioning. So let's go add them up. So help me here, guys. So I'm going to put my neutral load. My neutral load was 219 plus 19 plus 1.5 plus, and I did not do this step, plus 50 plus 24. Right? Am I right? The only thing we dropped is just the 265.8. Okay, what? Did I miss anything? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Any suggestion? How much? 313. 313.5 kVA. 313.5 kVA. Okay, that's a piece of cake, huh? Let's find the amps. I neutral, the current for neutral equal 313.5 K. Divide this by 1.73 times 480. What do you guys come up with?
377.5.
377.5 amp. Anybody, any second? I need a second before we move on. Second? Just move, Chad. Sounds like government work. Second, move it. Right? Okay. Now here's where you can, guys, here's where so I neutral was 377.5. Guys, do you see the I neutral 377.5? Gentlemen? And then from here, I can direct more too, based on 220.61. The first 200, what do you do with them? Leave them alone. Anything higher than 200 minus 200, what do you do with them? 0.7. Who's my favorite friend is going to add 200 to the rest of them? This will be a plus.
324.
324? 324 amp. This is my demand neutral load. This is my demand neutral load. Demand. My demand neutral load. Did we get the second on 324? Okay, then 324 do I have an option other than paralleling it? I already parallel the phases. So divide by 2, what do you get? 150 some? 162? 162 amps. Take this one to 310.15 B16 table, 75-degree column. What do you get?
2 cents.
2 sets? Yeah, we're gonna have 2 sets of one conductor. What's the size? 2/aught AWG THHW. 2 sets of 2/aught. Now, if you came up with less than 1/aught, can you use this at 1/aught in parallel? No. If you came up with less than 1/aught and you're paralleling it, you're stuck with 1/aught. There's rules for paralleling, guys. You can't parallel this at 1/aught. We came up with 2/aught, then we're good. So that's the size of your neutral. Cool?
220.61 is written on there. Is it, I mean,
220, that will tell you to do the derating. 220.61B, we can always go to B here too. It will tell you that you can also derate anything higher than 200 by cutting it, anything higher than 200, you can cut it by 70%.
all right,
If-
well, on,
Okay.
oh, anything, okay, never mind. Okay,
Anything.
anything higher than 200%, you take at 7%.
Yeah, absolutely. So that's why we leave the 200 alone, and then anything higher, that's how the higher, multiply by 0.7. Cool? Last thing, last but not least, that would be number 6. Number 6 is, I would like you guys to do grounding electrode conductor. Size the grounding electrode conductor. How do you size a grounding electrode conductor? 250.66. So you're going to use, how many sets do we have? We have 2 sets, multiply them by 500 kcm. That will get you what? Get you 1000, comma kcm. Then the next step is you take 1000 kcm, take this one to table 250.66. That will get you, anybody? One conductor, 1/aught, A, W, and a G, T, H, H, and it's a say THH and no THH, THHW.
2 cents of one out, right?
No, only one.
Oh.
Only one. Okay, piece of cake. Let's make this a W, even though it's not very current, but typically they have translation. THH W. We're using W. Or bare, or this is doesn't have to be even insulated. The bonding jumper. We forgot the bonding jumper. The bonding jumper is going to be the same, right? Okay, when you're done, I'm just going to write the bonding jumper, which is going to be the same. Anybody knows why it's the same? Have we exceeded the 1100, the magic number? So it's going to be the same. But guess what? On the test, you might exceed it. Okay. Move, yes. Okay, so will that be number 9? Or we at number 7? Number 8. Oops. Okay, number 6. It wasn't 8. Number 6. Number 7. As main bonding jumper. This is 250.66 stable and 250.28. Right, 28A I think, or D1 tech, we just saw it. D and 1. You're good with these, throwing him like throwing bananas, man, all the way. Go. Alright. So let's do the math. I want to do it quick. 2 times 500 kcm equal 1000 kcm. Then there's a reason why I do it this way, guys. 000 kcm. Is it more than 1100 kcm? What's the answer? Yes. And then you delete the yes, and you say no. Okay? If it's no, then what do? Then all what you have to do is take the 1000 kcm, take it to 250.66, and that'll get you, what did we come again? One conductor? One out, thank you. 1 odd WG. T, H, H,
No,
W.
it goes to odd, sorry.
To what?
So the 1,000 plus it. Yeah, 1,000, it's too odd.
To what?
I was reading the wrong number.
It's all right. Next time we'll charge you for that.
Okay.
To what? So the grounding electrode, the same thing like the grounding electrode, we just did that. No, why did you get to 2 watt?
1,000?
Yeah, we
600 to 1,000 is too odd.
so that's wrong then.
500 is only 1 odd, but 1,000 is too odd.
Okay, so that one was wrong then. All right, let's change that one. Thank you. So up to 600 to 1,000 is 2 watt, yeah. So who gave me the 4 watt so I can deduct grades out of his? This is a 2 watt.
4 watt.
2 watt, right? There you go. It's between over 600 up to 11. Give you 2 watt. 2 watt cover. Okay? I'm gonna move it away. 2 watt. Okay. Any question, guys? Any comments? This will be your test, my friends. Main bonding jumper. No, 2.6. Okay, I have it here anyway. Why do we have it here? Okay. Okay. Any questions, any comments? Any questions, any comments, my friends? Why don't we take a few minutes, guys, and then I'll go over the theory in a second here. There you go. So we have the 2 watts here. Why did I delete it? Oh man. Let's take 5 minutes break, guys. Then we'll go from there.